In this video, we'll take a look at Fischer projections. So the objective of this video is primarily to show you how to convert between a skeletal structure and a Fischer projection. So first, let's define what a Fischer projection is. So this is a structural perspective such that the atoms that are on the horizontal axis are coming out of the plane. So they're kind of like wedges, like pseudo wedges. And then the atoms on the vertical axis are going into the plane. So that again, they are like dashes like in our skeletal structure. However, this doesn't correlate directly to the dashes and wedges that you'll see in a skeletal projection, even though they both represent the same thing, that they're either coming out of the plane or in the plane. But that can be a common point of confusion when you're converting these. So I'll go through the process, but don't automatically just see that a wedge in the skeletal definitely means that it's on the horizontal. In the Fischer projection, that's not necessarily the case. So here's an example to explain this a little bit better with a visual. So here we just have a Fischer projection. Again, this shows the tetrahedral carbon here, this sp3 carbon, such that the bromine is up, the methyl group is down here, and then OH and hydrogen are on the horizontal. So what this actually means in a three-dimensional structure is that this bromine is back, is in the plane, this methyl group is back in the plane, and the OH and the hydrogen are out of the plane. So let's look at a molecular model to represent what we're looking at here. So here we have a molecular model. So this is the same. So let me explain how these two are the same structure. So the green is a bromine, and it's back. It's in the plane. The methyl group is down and in the plane, and in the plane. So there. The OH group is out of the plane and to the left. So that's here. And the hydrogen is also out of the plane and now to the right. So this is the Fischer projection. This is the perspective that we're looking at. But now let's look at it from a Newman projection, right? So all we've done is rotate it here. Now notice that in order for this structure to be consistent with the Newman and the Fischer, you have to have it that it's an eclipsed conformation, right? Because if it's an eclipsed conformation and then you move it here, it puts such that these the methyl group is down and that these are both out of the plane on the horizontal, and then these are both out of the plane on the horizontal. If, for instance, it was staggered, so let's go back to our Newman and then make it such a staggered, just rotate the bottom bond. When you now look at this in the Fischer, this isn't critical in this particular molecule because this center down here isn't chiral, it's just a methyl. But notice that the horizontal has the OH out, the hydrogen out still, but now the horizontal on the other carbon has both of those hydrogens that are in the plane. So that will be an issue for more complicated molecules. So just keep in mind, I think it's best to draw your Newman first, that's eclipsed, and then it's very easy from your eclipsed Newman to draw the Fischer projection. All right, so here is our first example going all the way from the skeletal structure to the Fischer projection. So first, I always think it's best when you're looking at these different structural representations to start with a molecular model. So let's draw this, or let's represent this in a molecular model. So here we have it. So our OH is in the plane, and on this going up here, up and in the plane, that's here. There's this hydrogen that's not drawn. That is a wedge that's out of the plane. This bromine is in the plane, down and to the right. That's the green atom here. And the methyl group is now to the left and in the plane. Okay, so again, I think the first step here is to draw the Newman projection in an eclipsed Newman projection of what you have. So this is just a two-step process, but first let's draw the eclipsed Newman for this molecule. Okay, so if we just wanted to look at a Newman, simply all we do is rotate this out, right, like we've done previously, and it would be, depending on the methyl group, it can be staggered. Like this would be a more stable conformation than the eclipsed, but in order to draw a Newman, it must be eclipsed. So you just make it such that it's eclipsed, and any any particular conformation is fine for this. It doesn't make a difference. Your Fischer will look different, but it's going to have the same exact structure. Okay, so now once you have that, then you simply rotate up such that you put this carbon, oops, there. Okay, so now what we see is the OH is on the vertical and in the plane. The bromine is out of the plane to the right, and the hydrogen is out of the plane to the left, and then we have our methyl group. So this is the Fischer projection. So let's draw the Fischer projection now. So carbon, bromine on the coming out of the plane, which is the horizontal, and then a hydrogen on the plane, out of the plane that's on the horizontal, and then the OH is up and in the plane, and the methyl is up and in the plane. So again, in the Fischer projection, this is equivalent to the wedges on the horizontal like this. All right, and now I'll bring the model back. So again, our bromine is out of the plane to the right, hydrogen is out of the plane to the left, our OH is in the plane and up, and then the methyl group is in the plane and down. So this is the process. Now let's check that these are in fact the same molecule. So the best way to check is always with absolute configuration. So we have to determine if this chiral center is R or S, and then compare it to the Fischer. If they're the same, then it's the exact same molecule. Okay, so here's our chiral center. Now we have to determine what has highest priority. Well, bromine has a higher atomic mass and atomic number on the periodic table. So this is A. This is a higher priority than the oxygen. So that's B. And then the methyl group here is C, and the hydrogen is last, which is out of the plane here. So this looks like S. It's going counterclockwise, but the hydrogen is out of the plane, so it's actually R. So this one is R. So now, in order for our Fischer projection to be correct, it also has to be R. So again, let's look at our Fischer projection. Our bromine is highest priority, OH is second, methyl is third. This looks like S, but the hydrogen is out of the plane, so this is actually R. So this Fischer representation is a correct representation of our skeletal structure, and this is the process by which you convert between the two and then check to see if they are the same. It's all about absolute configuration. All right, for the remainder of the video, we will look at several examples going through this entire process from the skeletal to the Fischer projections. So that is our question here. Draw the following molecules from the skeletal structures to Fischer projections, and then the same process we did before, check that the molecules are the same by determining the absolute configuration at each chiral center. So again, I think it's best to start with a molecular model. So here is our molecular model that's consistent with this structure. So again, the OH is out of the plane, and it's out of the plane and on this carbon here. The methyl group is in the plane and down to the left like this. This bromine is in the plane and down there, and then the methyl group is in the plane like this. Okay, and then we have our hydrogens that are in the plane and out of the plane respectively on both of those carbons to finish out the structure. So now again, the first thing that we need to do in this process is look at our Newman projection in a eclipsed conformation. So if we just rotate such that we're looking at it like a Newman, rotate that a little bit to make it look better. See, that would be a staggered conformation. So what we need to do is rotate it such that it would be eclipsed. And again, it doesn't matter which one. I'm going to make it such that the methyl is eclipsing with the methyl, but again, it doesn't really matter. Okay, so here is our eclipsed conformation of the Newman. Now I will draw that. just as a reminder here. So we got our methyl group in the front carbon is down, like here. And then our OH is up and to the right. Our hydrogen is up and to the left. And then we have a methyl group that's in the back eclipsing, and the bromine in the back eclipsing, and a hydrogen in the back eclipsing the other hydrogen. Okay, so that's our Newman, our eclipsed Newman. Now, what you want to do is rotate this such that the horizontal is coming out of the plane and the vertical is going in. So like this is one such possibility, right? Because now we have our horizontal coming out of the plane, horizontal coming out of the plane, and this will be our Fischer. So now let's start with our Fischer here. So we have two chiral centers. So that is a vertical line like this with two centers. And then our OH, starting at the bottom carbon here, our OH is to the right, our hydrogen is to the left, our bromine is to the right, our hydrogen is to the left for the second carbon that's here. And then we have methyl groups on the verticals that are down. And again, remember, the verticals are in the plane, and that's why they are going in the plane and vertical, and the bromine and all this horizontal is out of the plane, which is why this is the correct representation. So now let's confirm that this is in fact the same structure by looking at the absolute configuration. So let's look at the absolute configuration of our skeletal first. So here we have two chiral centers, this carbon and this carbon. So at this one, the highest priority is the oxygen. Then we have to compare this carbon to this carbon. Well, this carbon is just bound to 3 hydrogens. It's a methyl group. This carbon is bound to a bromine, so that's going to be higher priority. And then this is C, the methyl group, and then the hydrogen is in the back. So this looks like R. It's going clockwise, and the hydrogen is in the back, so we don't have to switch it. So it is in fact R. Now I'll use a different color for the other chiral center to try to make it as clear as possible. So again, this bromine is highest priority. And then now we have to compare this carbon to this carbon. Again, it's a methyl compared to a carbon bound to an oxygen now instead of a bromine. So this is B. And then C is the methyl group here. This looks like R. The hydrogen is coming out of the plane. It's on the wedge. So this is in fact S. Now let's go to our Fischer and check if this is the same. So we'll start with this carbon, which should be S if it's the same as this molecule, because that's the one bound to the bromine is S. So let me use orange to be consistent with that carbon. So bromine is A. Now again, this is B because this carbon bound to the OH is higher priority than the methyl. This is C. This looks like R. The hydrogen is on the horizontal, so it's S. So that carbon is in fact the same in the Fischer and the skeletal. And then let's look at the other one. This is the highest priority, the OH. Then the carbon bound to the bromine is B, and then the methyl group is C. And this looks like S. The hydrogen is on the horizontal, so it is actually R, and this perfectly checks out. So this is a correct Fischer representation for this skeletal structure. Again, there are multiple that you can draw. If you rotated for a different eclipsed Newman, when you started, you're going to get a different Fischer. But again, it's all correct as long as your absolute configuration is consistent with all of the possible representations. All right, here we have another question. So again, I think it's best to always start with your molecular kit, your molecular model. So here we have our structure. So our carbonyl, that's the C double bond O here, and then the hydrogen on that carbon. So then this OH is in the plane like this, and this OH is in the plane like that, and then our methyl group is in the plane as well, up to the right. Okay, so now again, our first step is to draw the eclipse Fischer, or the eclipse Newman projection rather. So if we look at this just as a Newman, this is kind of staggered. So let's make it just so it's eclipsed like this. There we go. So now here is our eclipsed Newman. And this one is hard to, it won't sit just because we have our carbonyl here, right? So essentially what we're looking at is we have an OH that's eclipsing with the carbonyl of the aldehyde. The methyl group is eclipsing with the OH here, and the two hydrogens are eclipsing. So I'll draw that here. So our OH was at the front carbon and it was down. And then our methyl group was to the right. And the hydrogen was to the left. And then our aldehyde was eclipsing the alcohol, so CHO, that's our aldehyde. And then we had the alcohol in the back eclipsing the methyl group, and then the hydrogen eclipsing the hydrogen. All right, so let's bring back the molecular kit just to show that this is the same. So if we look at our front carbon here, there's our hydrogen up and to the left, and then the methyl group up to the right, OH is down, the aldehyde is eclipsing the OH and the back carbon is eclipsing the methyl group, and the hydrogen eclipsing the hydrogen. Okay, now we want to rotate this, so let's bring this back. We want to rotate this such that we get the horizontal coming out at you. So if we rotate it like this, that's exactly what happens here. So the horizontal comes out of the plane with the methyl group out of the plane, hydrogen out of the plane, OH, hydrogen, and the carbonyl and the OH are in the plane on the verticals. Okay, so now that we saw that, let's draw this. So again, to start your Fischer, you should just have vertical line, and then horizontal is the number of chiral centers. So here we have 2. So on the first one down, so looking at this again, the first one at the bottom is a CH3 methyl group on the horizontal, and a hydrogen at the left, and an OH in the back. And then at the top carbon, we have a OH, a hydrogen, and the carbonyl. Okay, so now again, let's check this. So here's our carbonyl, the top carbon, and then this carbon, OH to the right, hydrogen to the left, hydrogen to the left, methyl group to the right, OH in the back on the horizontal. So from our molecular model, this seems to be correct. So now again, let's check our absolute configuration and make sure that this is the same. So here's our first chiral center. The oxygen is the highest priority. Then we are comparing a carbon bound to an oxygen and a carbon bound to 2 oxygens. In our Kahn-Engelb Prelog rules, we consider double bonds as being bound to more than 1 atom. So this is considered B then, by those rules. This is C. So this looks like S. The hydrogen is in the front, so it's R. Okay, let's do the second center now. So the OH, again, highest priority. Now it's a methyl versus a carbon bound to the OH, so that's B goes to the carbon bound to the OH. C is the methyl. This looks like R. The hydrogen is in the plane, so or is coming out of the plane. It's a wedge rather, so it's S. Okay, now let's check this position again. So that first carbon at the top is this one here. It's R. So this OHA. Then the aldehyde, then this carbon bound to the OH. That looks like S, the hydrogen is on the horizontal, so it is R. So that one is the same. Then if we look at this position, this carbon, so we have an alcohol directly bound to that carbon, then a carbon bound to an alcohol, higher priority than the methyl, that looks like R, the hydrogen is on the horizontal, so it's S. So if we go back here, RS, RS, this is the correct or a correct Fischer projection. Again, there can be many depending on the eclipsed Newman that you draw. All right, here we have another question. So this molecule has 3 chiral centers, and it becomes difficult to show the eclipsed Newman conformation when you have 3 chiral centers, because all of the potential carbons need to be eclipsing each other to get the Fischer to look just right. So it's best here to do some kind of a shortcut, which after you are comfortable with visualizing this stuff after the first few examples, this is how I recommend you do this, is now you just draw the Fischer, skipping the Newman, and then make sure that your absolute configuration is correct. So what I mean is here we have 3 chiral centers, 1, 2, and 3. So let's just go straight into the Fischer, where we have 3 horizontal axes for those 3 carbons. And then we have at 1, we have the aldehyde that's here, attached to 1, that's this position. And then 2 and so on. And then here all the way at the bottom, we have our OH that is a part of the vertical, right? And I put those as vertical because they aren't a part of this three-dimensionality here. So now, basically, you decide where the OHs need to go, and this is always going to have to be checked by the absolute configuration. So I'm just going to say that the OHs go on the right and the bromine goes on the right, and we'll check. This is likely incorrect. So here we have one possible Fischer projection. Now we need to determine all the absolute configurations to check if it is consistent with our skeletal structure. So again, at 1, the oxygen is the highest priority. That's directly bound. This carbonyl is a higher priority than the carbon bound to the OH. So this looks like S. The hydrogen is out of the plane. It's a wedge. So it looks like this. So that is R. Now if we move to the next carbon, the oxygen is the highest priority. Then we have a carbon bound to a bromine or a carbon bound to an oxygen. So the carbon bound to the bromine is a higher priority because the bromine is a higher atomic mass, a higher atomic number. And then C is this carbon, and the hydrogen is in the front coming out of the plane. So this looks like S. The hydrogen's out of the plane like we said, so this is actually R. Then if you move to that last center, it's bromine versus an oxygen in terms of priority. Bromine has higher priority than the oxygen, and then the carbon that's bound to the oxygen. So I'll put the C over here. So ABC looks like R. The hydrogen is in the back, so it is R. So now if this is RRR, then this is in fact the correct structure. So let's start with our first center. We have an oxygen. That's highest priority. Then the carbonyl, then the carbon bound here. So 1, 2, 3, or ABC, that looks like S. The hydrogen's on the horizontal, so it's R. Then we move to the next center. Again, oxygen is higher priority. Then the carbon bound to the bromine. Then the carbon bound to the oxygen. So that looks like R. The hydrogen's in the plane, so it's coming out of the plane rather. It's a wedge, so it's S, right? So ABC looks like R. You have to switch it because of the hydrogen. Then the last one, we have bromine, highest priority, then oxygen, and then the carbon bound to the oxygen up. So that looks like R. The hydrogen is on the horizontal, so it's S. So now what we need to do is use this rule that anytime you switch 2 molecules or 2 atoms in your molecule, you switch the absolute configuration. So what I mean is if I put this OH on the left and this hydrogen on the right, this is now going to switch from S to R. Same thing for the bottom one. So let's do that and then confirm that it does in fact result in the correct structure. So our OH, the first OH was correct. That stays on the right. This OH now needs to go to the left, and the bromine needs to go to the left. Again, because we need to switch our configuration. Since this is RRR, we want that to be the same. Here we need these 2 centers to be different, to be switched. So then we fill in our hydrogens and the rest of the atoms. Okay, and we know that first one is R, so let's keep that as R and not do the configuration determination again. But now let's look at this one and confirm that this does switch it to R. So the OH is highest priority, then the carbon bound to the bromine, then the carbon bound to the oxygen, ABC, that looks like S, but the hydrogen is on the horizontal, so you switch it to R. And then our last center, we have a bromine, highest priority, then the oxygen, and then the carbon bound to the OH. So ABC, that looks like S. We switch it to R, and that is RRR, just like the structure that we had. So one correct representation is this one here, which I'll now redraw without all of the absolute configuration stuff. Okay, and then this is R, 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 and that's how we know it's the same. So you can use this shortcut for any number of chiral centers, right? I think it's most clear to use the molecular model for the ones that are less complicated like that, but you can always do this guess and check procedure, and now there is no ambiguity between these two structures. They are definitely the same. All right, so here we have another question. So again, let's do the same procedure that we just did and start with just guessing about what our Fischer projection will look like. So again, we have three chiral centers. So we have three axes like this. We have a methoxy group is OCH3, OCH3 on the verticals. Those are these two groups. Right? And now our chlorines need to go somewhere. So let's put them all to the right. Again, it doesn't matter because you'll have to check. So we have it like this. Now let's determine the absolute configuration at each center. So we have a chlorine versus an oxygen. Chlorine is higher priority than the oxygen, and then this carbon is last. So ABC, that looks like R. The hydrogen is in the back, so it is R. Then we move to the next center. We have this carbon is bound to a chlorine, so the chlorine gets a higher priority. Then we have a carbon bound to a chlorine, carbon bound to a chlorine, and then those are the same. So you have to move to the next position, which is the methyl group, and the methyl group, those are the same. So this is in fact not a chiral center due to the symmetry. Okay, so then we move to the next center, the next carbon here, that is this one. And we have our chlorine is the highest priority, then the oxygen, then the carbon bound to the chlorine. So that's C. So ABC, that looks like S, and it is in fact S because the hydrogen is in the back. So as an aside, this is a meso compound, which contain chiral centers but have no chirality themselves, because the chirality internally cancels such that you have an R and an S group, and then this center is not chiral, as we determined based on the symmetry. So now let's look at the absolute configuration of our molecules here, or of the atoms in this molecule of the Fischer projection. So we have a chlorine, that's A. Then the bromine is B, and then this group is C. This looks like S, and it switches to R because the hydrogen is on the horizontal. The next center is a chiral, so we skip that one. And we go down to the last one. Chlorine, again, higher priority than oxygen. Oxygen gets second priority, then this carbon group up. So that looks like R. The hydrogen is on the horizontal, so we switch it to S. So this is the same. So you may be wondering, where do you put that chlorine? And since it's a chiral, it doesn't matter. You can put the chlorine on the horizontal, to the right or to the left, and since it has no chirality, it will readily interconvert between either one. So that is all I have for this video. I hope you learned something. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic suggestion or any questions about any of this, feel free to leave it in the comment section below, and I will get to it as soon as possible. So with that, I hope you all have a great day, and I'll see you in the next video.